So hello, everyone. My name is Megan Carter. I'm ESIP's Community Director. Welcome to this 2021 Earth Science Information Partners Innovation webinar. And this is part of a webinar series which follows ESIP's theme for 2021 of leading innovation in Earth Science data frontiers. We are delighted today to welcome Dr. Evan Burgess, lead data scientist at Airborne Snow Observatories Inc, to talk about data system and software development challenges at Airborne Snow Observatories Inc, which is a NASA research program turned private enterprise. And I want to say thank you very much to SAIC for generously sponsoring this webinar. If you're not familiar with ESIP, welcome. We are so glad that you're here, and I want to give you a very brief introduction. ESIP strives to be a leader in promoting the collection, stewardship, use, and reuse of Earth science data, information, and knowledge, and to be responsive to societal needs. So for more than 20 years now, ESIP has helped members of the Earth science data community to find each other across traditional boundaries, to leverage each other's expertise, and to work together on common data challenges and opportunities. To help Earth science data professionals to work together, ESIP fosters rich collaborative experiences, including numerous community-driven virtual collaborations, the ESIP Lab, which supports the development of innovative applied Earth science technologies, and through 2 annual conferences. You can see that our next meeting will be in July, online in just over 3 weeks. Our agenda includes about 40 community-contributed breakout sessions on a wide range of topics, including data stewardship, geosemantics, cloud computing, AI, machine learning, as well as 4 plenaries, including one on data from the Mars exploration program. And there will also be numerous networking opportunities. So we encourage you to join if you can, and you'll notice the save the date here reminds us that next Wednesday, a week from today, is the early bird registration deadline. So that brings us to today's webinar, and probably why you are all here. We are excited again to welcome Dr. Evan Burgess. He's a software developer and data scientist with an academic background in glaciology. Evan has worked with radar and LiDAR data, UAVs, atmospheric and land surface models, in situ data, and more. Through his work, he has developed innovative software, visualization tools, and cloud computing solutions that can accelerate data-driven discovery. Evan's PhD used synthetic aperture radar to discover widespread interactions between wintertime glacier flow speeds and climate. His postdoc distilled decades worth of airborne LiDAR data to understand glacier mass loss in Alaska in ways that were not previously possible. As ASO's lead data scientist, Evan works to advance ASO's processing pipelines, data analytics, and decision support systems. He holds a BA from the University of Colorado and an MS PhD from the University of Utah. With that, I'll pass it to Evan. A quick note to the attendees, please add any questions that you have into the chat box during the webinar, and we will address them as time allows.
Cool. Let me share my screen. Thank you, Megan. Can everyone see my screen?
Yes, it looks great.
All right, great. Okay, thanks much, Megan. I'm psyched to be giving this talk. I am, if you may have recognized my last name, my wife is Annie Burgess, who many of you may know as ESIP's lab director, and I've kind of been associated peripherally with ESIP for a long time, so I'm psyched to be giving a talk and showing everyone a little bit about some of the stuff I've been working on. I'm going to be talking about the company that I now work for called Airborne Snow Observatories. My title is Data System and Software Dev Challenges in a NASA Research Program turned Private Enterprise. I'm kind of intending this talk to just kind of tell a little story about the evolution of this program, which I think is kind of unique in the sense of this was ASO was a NASA JPL research program for a few years, and at NASA it quickly kind of moved, it achieved its research goals and moved into the kind of operational world, and then moved into the world of private enterprise. And in that process, not only did the technology move from the research world to the operational world, but all the people also moved from being research scientists into this operational setting. So I'm interested in talking about the technology and also some of the challenges in migrating a team to those two different environments. And anyway, I think it's a good kind of, I'll be interested in just kind of sharing kind of some of the anecdotal experiences that we've gone through, and I hope that that'll be interesting and informative, and we can chat about things more. So hold on, it's not letting me go next. There we go. So it looks like some of you on this call will know a lot about ASO, but I do want to give a little background about the science, just because it is very cool, and that's a lot of the cool stuff and innovative stuff that ASO is doing. Airborne Snow Observatories is focused on one very important subject right now, which is water resource management. In the Western U.S., the majority of our water comes from melting snowpack. It does not come from rain. And all that snow melts in a few months in the early spring, and then we have to store that water and figure out what to do with it for the rest of the year. And this is all complicated by the fact that the amount of snow that falls within any one year can vary widely by, factors of 2-3 times. And so in a place like the Western US, where there is essentially not enough water to go around, there is a tremendous amount of complex decision-making that goes into figuring out what do we do with the water that we have in our reservoirs? When do we release water? When do we hold water? And one of the things that I have learned in the past year working for ASO is just how extraordinarily gut-wrenching these decisions are with respect to what do we do with our water. The people that manage these reservoirs have to decide between releasing and not releasing, and a lot of times if you mess up that decision, it can result in farmers losing entire crops and losing their livelihoods. It can result in municipalities flat out running out of water. And on the other side of things, if you end up letting too much water out over a spillway, which can happen, then you can produce floods that can cause a lot of damage. There's the big Orville flood incident that happened upstream of Sacramento a little bit ago. So you can risk loss of life and property damage and things like that. So there's the decision-making process is incredibly complicated and has real serious impacts to society. So the best thing that we can do to help this process and figure out what to do with our water is in the spring, after the snow stops falling, to make sure that the water managers know how much water is up in those mountains and is likely to come down over the next couple months. And that lets them manage their reservoirs much more efficiently. And so the motivation for ASO is that the traditional methods for doing this are not very good. The way this has been done in the past is by using in situ data, primarily SNOTEL networks. These are point measurements of snow depth and density and so forth. And then along with these data, there's a lot of statistics and historical knowledge of these various basins and other, SNOTEL data over many years. And basically the traditional method uses these in situ data and historical data and stats, and basically will come up with estimates of how much water is going to come out to the mountains each year. This doesn't always work. Just as an example, this table on the right here is showing you forecasted inflows into Dillon Reservoir, which is in Colorado, and the observed inflow and the differences. And you can see that these kind of traditional methods, sometimes they work fine, and other times there are really, really substantial errors that cause big impacts to society. And one of the things that we're hearing from water managers is that as climate change is becoming more and more obvious, it's affecting weather patterns in ways that are basically making the historical record of what has gone on in these basins in the past less useful. And so there is a general decrease in the confidence of these traditional methods as climate change just sort of changes weather patterns and things like that. So there's a very, very big need to find a better way. And that's the motivation behind ASO. So how can we make water supply forecasting more robust? Well, we whoops, hold on. Instead of relying on these point measurements of snow depth, we can make spatially comprehensive measurements of snow depth across entire basins and entire mountain ranges using remote sensing. And we can rely on spatially distributed and physically based models as opposed to empirical and statistical models. And what this does is it removes our reliance on historical records. So when we're trying to figure out how much mountain or how much water is in the mountains this year, we are not relying on assumptions that it is similar to years in the past. And this is the whole idea behind ASO. So the ASO program started in JPL, I'm going to mess this up, a little less than 10 years ago by Tom Painter, who is now our CEO. And the idea is relatively simple. We have an airplane. We have two sensors on it. One is a scanning LiDAR altimeter, and we also have an imaging spectrometer. The altimeter gives us terrain height with a resolution about 1 meter. We're getting 1 point per meter, more or less. And the spectrometer is used to get the spectral properties of the snow, and for that we can retrieve the snow albedo, which is very important for modeling how the snow is going to melt over the course of the season. What else? So I mean, the idea is pretty simple. The way this works is we will fly over a mountain range and survey it in the summer when there's no snow, and then we come back in the winter and resurvey, and we can subtract that elevation model that we get in the winter from the one in the summer, and that difference represents the snow depth. It's a very simple idea in theory, but it ends up being extremely complicated because to do this right, we are really pushing the instrumentation, specifically the LiDAR, to its absolute limit. And so ASO has been working actually with Regal, the LiDAR manufacturer, to 2 times now basically construct one of the most advanced commercial LiDAR system available. And that's one that we're actually flying with this year. So in addition to the instrumentation, we've really had to innovate a lot of the science code and do a lot of things that other people are just doing with commercial software, but we've had to do on our own to really refine the uncertainties and allow us to, just get more accurate data and get it on over very large regions. I think that's all I was going to say there. So when ASO is all working, it produces some really, really cool data. So this is an example, a 3D view of the maroon bells in Colorado. The color here is the snow depth. And you can see red here is more than 5 meters of snow. Blue is less snow. And so the cool thing I think about when I look at this picture is you can see how much more information a water manager has at their disposal with respect to knowing how much water is in their basin than if you just have a single, met station somewhere in this picture and otherwise have to guess and infer what's going on throughout the rest of the basin. So this really takes away so much of the guesswork and the risk associated with decisions in water management. Okay, so ASO has gone through a pretty complex process that I was not privy to. I was hired on afterwards, and sounds like Kate who is on this call, was closely related to this process. But so basically what happened at ASO is that the research goals were achieved very quickly within a couple of years, and what just kind of organically happened was the same team that developed the technology started to just produce the data products for water managers as they saw them is extremely useful. And over time, NASA has a program or a process essentially that allows research programs to move into an operation, basically to separate from the government world and move into a private enterprise. And that is ultimately what happened here. And ASO is now Airborne Snow Observatories Inc. And we're a public benefit corporation. So we're for profit, but we've made a the company has made a strong commitment to provide a public benefit. And a big piece of that is making sure that our end products are public to the extent that we can arrange that to happen. So that's a big piece of it, and therefore data distribution is a big part of what we're going to be doing. So the way this is working, my computer is going very slow. Okay, so yeah, back. So the way that this is working now is that as a private entity, we are contracting with all sorts of different agencies, local water management agencies, state agencies, municipalities, hopefully eventually federal agencies. And we are contracted to fly specific basins that are of interest for water management. We'll fly one what we call a snow off flight in the summer, and then usually multiple snow on flights as the spring melt season evolves. And we use all the technology that's been developed. We run the data through these pipelines. And one thing that's been proven with its time at JPL is that when we produce one of these data sets, as you can see on the right here, our estimated snow water equivalents for a basin are usually within a few percent of what is observed ultimately at the end of the season. So it takes away so much of the guesswork in water management. So what was I going to say? So, and so in addition to processing this data and running it through a really extensive validation process, we're also committing to turning the data around really fast within 72 hours. This is actually a really big deal. When I've worked with other LiDAR companies in the past, it's fairly standard for companies to want at least a month to turn around airborne LiDAR data. So we're really setting a really high bar for ourselves there, and the speed of the turnaround is really important for water management decision making. And so kind of how this is evolving is, right as we're privatizing and gearing up to scale and everything, the need for this is becoming very apparent. Just this year has been a horrible year for snowfall in the Western US. And this technology is starting to become, well, let's just say that other places throughout the world are starting to become aware of this technology and starting to want it. So we're really in a tight spot here and trying to scale up and help as many places as we can as fast as possible, but also do things right so we can grow this in a sustainable way. And so my position at this company has really been in updating the technology, getting all this science code in a scalable place, and so we can provide these services to many different places. So getting onto the data and compute side of things, the tricky thing, and this is the truth about a lot of research programs, is that all of the code and all the technology that was developed was not developed to be super scalable or super reliable in an operational sense. It was built as research code. It was built for proof of concept, and over time it was slowly made into operational code, but the team has never really had the time to sit down and say, okay, how can we design this system to be super scalable and ready for an operational life. And so that's what we have been working on in the past year. Up until last year, all the software was developed in a proprietary language called IDL, which is widely used in remote sensing. But yeah, anyway, yeah. So it has, so a lot of the code has limits to how much we can parallelize it, which really limits our speed of processing. There's still manual steps. There's manual steps that require not just anybody but essentially a PhD in snow science to go through. The pipeline works, but we still encounter errors, and in those cases, we've often solved them ad hoc as we're processing this data in real time. In the past, data has been archived at JPL and internal servers, and the delivery has basically been through emails and personal communication. So, this worked very well. It gave a lot of people late nights, but it essentially worked on the scale of a few basins when ASO was going through proof of concept in California. When we're looking at scaling up, the amount of the scale of the tech debt was becoming very apparent. So, now we're looking at, in the next 3 or 4 years, flying 3 to maybe even 10 times the amount of area that we've flown before, and that adds a ton of complexity in the sense that it's not just flying more, but this is going to require multiple planes, multiple instruments. We're going to be switching instruments from one plane to another, which produces all sorts of complications. The reliability and the speed of the turnaround is becoming more important. We lost all of our computing hardware when we left JPL, which was a good and bad thing. Now it's forced us into the cloud, which is turning out to be great. And then the other tricky thing is that we're scaling up very quickly, but in the process of scaling up, there's all these other problems. So we're basically having to scale this technology up before all of the science is really fully matured. So we're having to do software development and science development all at the same time, and that's added for a lot of kind of, I would say, somewhat unique challenges. I think in a lot of cases when DACs or other entities are trying to operationalize science, you get the science to a matured point, and then you clean it up and turn it into a NASA data product. We kind of have to kind of move both of those processes together. So this is kind of a grab bag, but I kind of wanted to go through some of these things that I'm talking about more specifically, and some of the challenges we're facing, and how we've gone through, or how we've resolved them so far. Scalability is something that is always a subject of conversation, and for us, actually, AWS has just been so fantastic that the compute and the data has actually been one of the easier challenges. The newer challenges not the newer challenges. The bigger challenges have been dealing with the complexity, other physical complexities of scaling something like this up. We have to prepare for flying multiple planes on the same day. Some of them may be working in coordination to cover the same area. Other planes may be flying in different parts of the world. We have different instruments on each planes. So every time, an instrument gets put on a plane, it has to be recalibrated. So a lot of the things that used to be things that we could just hard code into software, like an instrument calibration, now all of a sudden we have to keep track of this in a very dynamic way. So yeah, keeping track of all sorts of physical things associated with scaling something like this up. And the other big thing has been metadata and search. I've worked with a lot of satellite data and then airborne data, and satellite data is just so clean and uniform, and airborne data, every single time a plane takes off, something changes. We have instrument configuration changes on every single flight. Instruments change, planes change, and so there's so much more to keep track of. It kind of feels like you have a new sensor every single time the plane comes up. So there's a real need to organize all this and be able to search through all the flights that have happened and figure out, if we want data for this basin, what are the flights? When has the plane actually covered this spot? That's a simple question that we weren't able to answer a year ago. And another thing that I think is common in a lot of research moving to operations is our team. I say ASO stubbornly innovative. We're all scientists, we're engineers. It is impossible to tell people to settle on a specific algorithm and call it good, and then we're just going to run with that. Throughout a operational season, it's not infrequent that we have to change code either to fix a new problem or just someone thinks they have a better way to do something. So there's a need to build a pipeline that's highly automated, but we also have to make it super flexible so we can change something, add a new task, a new step to a pipeline, and the pipeline will basically work, and we need to be able to do that within a matter of an hour or something like that. Another interesting thing is, the traditional in software development, the traditional way to deal with fast and continuous development is have separate dev and production environments, and that usually works. In our environment, as I say here, the line is between dev and production can be blurry. Basically, we can be running a flight that is a paid-for production flight and need to turn around 72 hours. We run into a new problem, say with the instrument on a new plane, and so we have to, in real time, come up with a fix for it, rerun pipelines, and then so a data set that we maybe initially thought was a production data set becomes either bad or a development data set, and we need to change our minds with respect to what is the good official data set versus what is not. So we've kind of had to develop I think, some unique ideas as to how to deal with that problem. And a lot of that just comes with, pushing this technology, forward as fast as possible. A few other things that we're dealing with, like certain areas are needing different pipelines than others. When research was focused on just a few individual basins, there were a lot of consistencies with respect to projections and even geographic things like vegetation that now we need to keep track of and treat different areas in different ways. We have proprietary software that often requires windows, and one actually has a GUI. So figuring out how to automate that type of stuff is really tricky. And the other thing is we're really trying, even though we're a private entity, we're trying to work with researchers as best as possible, some of which are working for ASO. And so I've really been focused on trying to make sure that the software and tools that the researchers are using to do their own R&D is as close as possible to what is actually running the pipeline, and that really just facilitates in that process of getting new research out into the operational world as fast as possible. So I'm going to kind of go through a couple of examples of how we've dealt with that. So one of the big things that we've been working on is just a move from this language called IDL into the open source world, and the simple translation of the code has gone fairly smoothly. One of the big challenges that I've been dealing with is, and I think we're going to do better this year, is, if you have research scientists who have written code in their native programming language, and then you say, all right, we're going to parallelize it and move it into open source, it's great, it runs faster, but then all of a sudden that researcher, the person who has the ideas behind that technology, loses the connection. They lose the ability to continue to modify it unless they are fully educated in Python and all the technology that the new implementation is using. So I've found that in addition to teaching all of our scientists Python and open source, that we really need to persistently work with them to push them all the way into the open source world. It's often, in my experience, it's often very easy to sell open source. The idea is it's an easy sell to software developers, or not software developers, but scientists, because they don't like to be reliant on code that they can't get in and mess with. But then once people start working in Python, some of the realities of package management and getting familiar with all these different packages become apparent. And it's also, if you're beginning Python, it's not easy to dig into one of these packages and actually change something like we idealistically like to think we can in all open source. So it's been really important for us to not just translate the code, but also make sure that the whole team at least understands how to continue to contribute to the technology as it stands in the open source world. What we currently have implemented in AWS is pretty simple, but it's been working very well for our case. All the processing is done in EC2, and we have a data management system that consists of all the data being on S3. And we've set up a excuse me, one sec. We set up an API with the Amazon API Gateway and AWS Lambda. It's a Flask API, and that is referring to a PostGIS database. And so the idea is, one sec again. Yeah, so we can use this API. Any computer can query the API to figure out what data is available, and I'll show you an example of that search in the next slide. The API will return a list of S3 objects that EC2 instance or laptop, frankly, can go in and pull from S3. And then we have an additional process where an EC2 instance, if it runs a step in a pipeline, it has a new data product, it'll hit the API again. The API will store all the metadata and basically confirm that it's okay to push that file up and give it a key, and so that exchange thing goes directly up to S3. In addition to this, one of the things that has actually really helped our team, because a lot of our team was not familiar with the cloud initially, and so our pipeline is now all in Linux and yeah, is in that environment. But we have there's been steps, and what we have done is set up Windows instances with just remote desktop, and it's a very simple thing, and it allows people to use GUIs in the cloud environment. But what it has really done is helped ease the transition for a lot in our team into the cloud, get familiar with it. It gives them a place that they are comfortable with, and that has really helped us utilize all the data on S3 and just kind of pull people into that cloud environment. And that's been really helpful. And the other cool thing that we've done, so we're a strategic partner, or one of our strategic partners is Esri. And so we don't have a good front-end developer on our team. And so as we've been working with some Esri developers to build a front-end, or build a website and data portal using ArcGIS Enterprise. And what I've been really psyched about is we've been able to work with Esri, and we've been able to produce a slick pipeline that it's open source, it's all our code. And at the end, when we produce data products, we can push them to S3, we can push them to a specific bucket, which constitutes the ArcGIS data store. And then it can automatically show up on the ArcGIS Enterprise data portal. So it's been a really slick way for us to utilize Esri and all of the image services that they have, and not have to worry about a lot of the front-end web development, but also keep all of the science in our own open source world. And that's been very nice and worked well to meld those two things together. We have started getting to the point where we need to use auto scaling and use a workflow manager like Apache Airflow. We're going to be doing that more in the next year, but AWS has some really big instances. So in a lot of cases, we've been able to work on a single big machine. Okay, So our search, we've set up the syntax actually looks, the more I see talks on Stack, our syntax is not very dissimilar from what you get with Stack. But basically we can query our API, we can select data based on any one of a number of parameters like flight dates, planes, specific instruments. The granule class is the type of file, not like HDF or GeoTIFF, but the actual type of data that is in it. So this example, we're looking at a filtered point cloud, a terrain model, whoops, or an albedo file. We have a kind of a unique versioning system. I'll talk about that in a second. But we can also select by, data that overlaps a specific basin or a bounding box, just like anything else. And so one challenge that we've had is we right now are storing all of our metadata in in an RDS table structure, and as we get this to the point where it's more mature, we're starting to keep track of metadata that does not fit into an RDS table system. And so we're toying around with, well, do we store more metadata in JSON that sits in RDS tables? Do we store it in XML? Do we need to use something like MongoDB? But we want to find a way to get all the metadata retained, but also make it searchable. And that's an ongoing challenge. Yeah. So this example. So basically, what we built is a Python package that allows us to kind of smooth over the process of moving data to and from the data management system in S3. You can select a specific granular file by its using that search, and then you have an S3 path to that specific granule, and then this class it manages the file naming convention for us, so it tells us what a good file name for it would be. It keeps all the metadata like the file extent, and then to deal with this versioning problem, when I was talking about us having to deal with data sets that might switch from being an operational data set to a development data set, we have a concept of we have a table in the database called our run table. And so whenever we run a pipeline, we get ourselves a new run ID, and that is associated with a text description of what that run was. So we could say, a routine run of this pipeline for this flight. And then that run ID gets attached to all the data that comes out of that pipeline. So in this example here, we have a file that has a run description that says it's rerun of a pipeline with improved regal bore sight calibration. So that tells us, okay, we actually ran this twice, and this one we have a better bore sight, and then we have a method or an attribute that tells us that this is the official one and not a one that someone else is using for R&D, but this is the official one that we're distributing. And it also helps us pull and push from S3. But anyway, this structure of allowing us to attach a fairly extensive description is very similar to Git and software, but we're kind of attaching that to the data as well, and allowing us to change it. So if data goes from being good to bad, we can change that run ID description, and it applies to all the data in that run. Another thing that we've done is we've in an effort to make the pipeline capable of changing very quickly, we have a table where we're keeping track of all of the various different types of data sets or granules that we could generate, and we keep track of the file naming conventions, both for a local file and where it sits on S3. And so what this allows us to do, if we add a new step in the pipeline, all we need to do is add the new types of data that step will generate into this table. And that keeps track of the file naming conventions. It keeps track of what all these files are. It allows us backward compatibility if file naming conventions change. And this has been really, really helpful as the pipeline becomes more and more complex. Our pipeline now produces over 170 different types of files before we finally come up with the end product. So there's a lot of moving parts in there that we need to track. And the other thing that we've talked a lot about this year is separating what I call the science code from everything else. So a lot of the original software, and I think this is very typical in science research-based code, is the data management stuff kind of gets intermingled with the science. And so what we've kind of done is separated all that code into those two different groups. And we have a process where we can take just a very rudimentary script. If some researcher gives us a new procedure just in a script, we can take that, we turn that into a simple function with just a couple basic rules about the input arguments and input needed files and those types of things. And we can wrap it in a class that allows us to take that function and not only parallelize it heavily, but also take advantage of all of the, basically work with the data system. So search data, well, here, just in this example here, what we can do is we basically put together all sorts of metadata, the input files and output files that the function needs, the function itself, arguments, the get version, so the exact version that we use to run it, and time. Then we go ahead and pull all the files, and then we pull all the files, we execute the code, push up the results with all the metadata, and then we manage error handling for a parallelized run and do cleanup. But the basic idea here is that this single class lets us take any old generic function and within 20 minutes be able to get it in the pipeline, have it work in a parallelized environment, and even a distributed environment on multiple machines, and handle all the metadata. And this has been a really helpful way for us to really get new code out and working real fast. Oh yeah, so one problem that we've kind of been facing that seems to be somewhat unique, maybe this is unique to, I don't know if this is unique to our case or unique to earth science in general, but when we start these processing pipelines, we don't necessarily know what the workflow or the pipeline will look like until we're part way through the pipeline. So when a plane comes, the way that we've parallelized all this is by tiling. And we don't know until we got the data up and processed it to a certain point, we don't actually know where the plane was and where it flew. So we don't know how much we can parallelize it. So we're trying to figure out ways that we can have a workflow management system like Apache Airflow, but deal with the possibility of changes to that workflow as the workflow is progressing. And that's a challenge we're still working on. What am I doing on time? Oh, I'm late. Okay. Very quickly. So ASO, we're with respect to data distribution, we're kind of unique in the sense that this is a private company. The data is paid for by all sorts of different entities. We advocate to make the data public, but that advocacy doesn't always work. So some of the data is private, and so we have to distribute this on our own private website. We want to maintain best practice. We want to give our data DOIs. But we can't do it, we have to deal with permissions in certain cases. So how to do this best has been a challenge for us. And working with Esri, we've been able to not only distribute the data on a web portal, but we're also working on some decision support systems that allow people to look at data and we're starting to put together visualization tools that allow people to just make decisions without having to download the data and analyze it on their own computers. And so these tools are working with a combination of Esri, but a lot of this is open source. Like the plots are going to be Plotly plots and hitting our own Flask API, and yeah. So anyway, it's going to be a kind of a cool mix of Esri technology and open source. These are just wireframes, so this is not built yet. And so lastly, I mean, basically there's kind of just been a brain dump of all the things that we've gone through. Like when I think about what's gone over the past year, like the big things that I've learned and you know, been working hard at is, you know, if you're trying to operationalize science, the more that you can slickify that process of getting a domain specific research scientist ideas into an automated system and get the data that is produced from those ideas into a searchable environment is super, super important. I think there's been a lot of cool technologies like Dask and so forth that allow us to take very simple code and parallelize it in big ways. But another piece of that is making sure that whatever comes out of those sort of sandboxy projects becomes data that is searchable and usable later. And basically, you know, in science, there's a lot of, you know, you do some sort of sandbox analysis and it's cool and interesting, and then you let it go. And then 3 months later, you get some new idea, and then you want to start over where that left off. And so making sure that all that stuff is accessible is really, really important. And that's what we've been working hard to do. And the last thing is just really, really pushing as you move stuff into the open source world and making sure that the researchers who have developed the science not only are trained in the open source technology that is now being used to implement it, but that they are persistently supported in moving themselves fully over into that world. Anyway, that's all I have. I didn't leave much time. I apologize.
That's okay, Evan. Thank you so much for that really informative, very generous presentation. You really, you know, got into the weeds of what you've been working on, where your successes have been, what innovations are still needed. I liked your use of the term stubbornly innovative. Thank you for that presentation. So I will turn to the chat where we already have a few questions for you. So we'll try to work through these. The first is from Matt Hansen, who's asking the first obvious question, why not stack? He says a stack compatible catalog and API would allow the use of the growing family of existing open source tooling.
I think the simple answer to that is time. I think we're headed in that direction. Yeah, I think so. I'll say that's a tech debt situation in that we are developing that quickly. But I think you know, the way this process is going to have to work is that, you know, best practice in technologies like Stack, you know, are over here, and we are going to be moving in that direction. And the question is how and when to adopt best practice and yeah, how to make that transition. So I think yeah, anyway, we're definitely moving in that direction.
Hey, just a little follow up on that, Evan. Does that mean that this is Rich Signal? Does that mean that you know, adopting the best practice is harder? I guess it does, right?
I mean, not always, but in cases, I mean, yeah, it certainly is. And there, yeah, I mean, yeah, I guess the answer is it depends, but you know, everything is getting pushed so fast in our case that, you know, fighting tech debt is a constant battle. And And so, you can, there's so many open source solutions out there, and you can look at them, and if there's an obvious, in certain cases it's obvious that yes, we need to use this. In other cases, code is half built and you just kind of go with that direction, and that's just tech debt building up. But yeah, so in someone like my position, I'm constantly just trying to see, like, where's the next best place for me to move us into best practice. And so it's a evolutionary thing that will probably take a while.
And maybe it's a time scale thing too, right? Like,
yeah,
it may help you to go to stack in the medium term, but you've got a deadline or for 2 weeks from now, and you just have to do something, and you don't have time to figure out how to do it in stack, something like that.
Yeah, I mean, yeah, that's the reality. I mean, but the thing is, I mean, that's tech debt building up for you right there. But it's there's, I always think about tech debt as a bad thing, and going for the quick fix is always a bad thing. But the company is advancing. We have a certain amount of growth that needs to happen, and the system that we have now is very similar to Stack. It works. It's not causing problems yet, so that's kind of where we are. And so I'm more focused on the aspects of things that aren't working at the moment. But I mean, yeah, it's prioritization and just figuring out how to tackle things one at a time.
Yep.
Thanks for addressing that question, Evan. Let's move on to the next one. Are you encoding the metadata you want to search into the geotiff metadata? Zach is wondering if you could do that and then use Athena to do the metadata query if response times on the order of seconds are acceptable.
I'm not doing that. I'm not familiar with that. So who asked that question?
That is Zach.
Yeah, this is Zach Fleming. I'm on the AWS Open Data team.
Oh, cool. Okay. I would love to chat with you. Let me know.
Yeah, I guess my main question is sort of like, you have a lot of database technologies that are sort of designed for, I would call them like sub-second queries to be able to return the metadata. Is there any real reason for that? Or do you think things on the order of seconds, tens of seconds would be acceptable for a lot of these use cases?
With respect to reading metadata, the tricky part is when we start to get these larger extents, there's a lot of geotiffs that you would need to query at one time in case. Well, I mean, I don't know what a lot is, but maybe we would need metadata from 300 to 1,000 geotiffs at once, and we can parallelize that, but in my experience, you can only parallelize it to a certain limit. Or
I guess my question is more sort of around the user experience and like what users are expecting when they run these queries to get, all of the
I mean,
geotiffs in an
no,
area.
a couple seconds is fine, but yeah, the trick is that certain cases we need to query a whole bunch of them.
Gotcha.
So, yeah.
Thanks.
Yeah.
All right. Yashing Wei, who represents ESIP's information quality cluster, is unsurprisingly asking how uncertainty or quality information is established and represented. Is it part of the metadata?
So uncertainty is a really, really sticky point with this whole methodology, and it's something that we are constantly working on. The short answer is we don't know our uncertainties for any one specific data set. The way that uncertainties are generally, this is a big question. There's a lot of work we do with determining the uncertainty of the actual LiDAR data. So using ground control to make sure that the terrain matches the existing ground control that we have. But then there's in mountainous terrain, there's all this fuzzy stuff that happens when you're acquiring data in vegetation. where, you know, we get a point and now we're not looking at the uncertainty of the instrument, but we're just looking at weird stuff with did the LiDAR shot happen to hit a bunch of leaves and not get all the way to the ground surface, and that type of stuff ends up being the biggest source of uncertainty in our data set. So what we do now is when we get our final estimates of snow depth, we compare what we think the snow depth is to the few isolated places where we have snow tell stations, and we can compare those. And we also can look at basically where our snow depth model, or how well our snow depth model matches what snow actually looks like from the spectral imagery. So basically, if we think there's snow if we think there's an actual snow depth somewhere, does it physically look like there's also snow on the ground? But beyond that, we don't have good solutions to figuring out what our uncertainties are for each individual data set, and that's one thing that we're actively working on.
All right, Evan, I'm going to steal the screen share back, but maybe as I'm doing that, you can answer this last question from Chris Crosby. Are there plans to make the raw data available, for example, the LiDAR point clouds? There are likely a lot of interesting reuse applications for them.
Yes. Well, no, let me say, not a lot. It kind of depends. This is probably a question more for our CEO to answer. I think in cases, yes, but in other cases, the point clouds are ending up as private. But Chris, I think you should, you know, chat with us more. So we should have a conversation sometime. That'd be good to have.
Yeah, I mean, we'd be happy to have a chat about how to potentially do that, and if we could play a role in that process.
Cool. Okay. Yeah, sounds good.
All right, wonderful. Well, there are a few more comments in the chat, mostly thanks from some of our other participants, Evan. We're all really grateful that you came to speak today, and thank you to all of our attendees for showing up and for actively participating by asking such great questions. This concludes our webinar for today. We'll be back with the webinar series continuing after ESIP's meeting next month, so likely we'll continue in August. To stay up to date on all things ESIP, including the announcement of our next webinar, and to learn more about the upcoming summer meeting, like I said, less than 4 weeks away, please subscribe to our Monday update mailing list. You can see the URL on the bottom left here. Finally, a note that this webinar was recorded and will be posted to YouTube shortly, so feel free to tell your colleagues and have them watch later. Thanks, everyone.